Okay, let's do an example with work. Let's say that you're pulling a sled with your little sister in it. If you don't have a little sister, you can put your dog in it. If you don't have a dog, you can put your imaginary friend in it. So let's say you're pulling a sled of mass m, and you're pulling with a force F pull, and it's a real sled on real snow, so there is friction. And I could make you calculate the frictional force using Newton's second law. Wouldn't be a problem. But just for the sake of doing a work problem and not so much a Newton's second law problem, I'll give you a value. Let's just say that the frictional force that is opposing the pull is 20 newtons. And let's say I'm pulling with a force of 150 newtons, pulling my sister on the sled. I guess it's my baby sister, because let's make the mass of the sled 20 kilograms. That's a little small, but whatever. I don't like to reuse numbers. Let's make it 30 kilograms. 30 kilograms. And let's say that I'm pulling the sled, I don't know, a distance d, or displacement d equals 20 meters. I've got to give you an what do you call these? Angle. Let's say that the angle that I'm pulling with relation to the horizontal is 25 degrees. And ask, what is the total work done on the sled? What's the total work done? So what I mean by that is let's simply draw a free body diagram, identify all the forces, and figure out the work done by each force and add them up. So first, free body diagram, and I'd love to ask what are the forces, but you are going to have to think of it on your own, and I will start by saying we know there's a normal force up because it's on the ground, it's gravitational force down because there's a weight, and that's F sub g. There's a pulling force at an angle, F pull, and there's a frictional force, FF. And I'll tell you right now that Fn is not equal to Fg because F pull is helping to reduce the normal force. You should see that from a Newton's second law point of view. That has no bearing here. But there is a free body diagram. We have now identified all the forces, and you could indeed call F pull a tension because my pull is on a rope. The rope is attached to the sled. So really that's a tension. But it doesn't matter too much what you call it as long as you understand that. Simply write down what is the work done, and I'm not going to bother with the F's, just work done by the normal force, what is the work done by the tension, what is the work done by gravity, and what is the work done by the frictional force. Boom, 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 da-da. And write down, you simply write down the definition of work, where you say it's the magnitude of the force times the magnitude of the displacement times the cosine of the angle, so the magnitude of the normal force times the magnitude of the displacement times the cosine of the angle. What angle? The angle between the normal force and the displacement. The tension, the magnitude of the force, times the displacement, times the cosine of the angle between the tension and the displacement, right? So these are all different angles. Gravitation, the magnitude of the force, mg, magnitude of displacement, d, times the cosine of the angle between mg and d. G and d. Work done by the frictional force, that's F. F is the frictional force, is the magnitude of the frictional force, times the magnitude of the displacement, times the cosine of the angle between the frictional force and the displacement. The N/D is just a shorthand that I'm writing for the angle between N and D, the angle between T and D. Okay. I've carefully drawn the arrows on the diagram, right? Or here, we can just go ahead and draw the displacement near this diagram, near the free body diagram. Shouldn't go on the free body diagram so as not to confuse the free body diagram, just so that we can compare the angles, so we can figure out the angles. So for example, what is the angle between the angle between the normal force and the displacement? Look at this and look at this. The angle is 90 degrees. What is the angle between the tension and displacement? Look at this and look at this. The angle is 25 degrees. What is the angle between gravitation and displacement? Look at those two. The angle is again 90 degrees. Look at the angle between the frictional force and displacement. What is the angle? It's 180 degrees. Look, it's 180 degrees, right? Be careful. Make sure you get those angles. And then we recognize, and I did that quickly, but I'm just going to go ahead and say, first I'm just going to do the angles and say, okay, this one's 90 degrees. This one was 25 degrees. This one was 90 degrees. And this one was 180 degrees. All right, and say, so I don't even have to worry about what the normal force is because the cosine of 90 degrees is 0. Work done by the normal force is 0. I don't have to worry about what the weight is because cosine of 90 degrees is 0. The work done by gravity is 0. You should have seen that already, that gravity and normal force don't do any work because they have no component in the direction of displacement. So all we have to calculate is the work done by the tension, which is the force of tension, which is 150 newtons, and times the displacement, the magnitude of the displacement, times 20 meters, times the cosine of the angle between those two things, which is 25 degrees. And then the work done by the frictional force is equal to the magnitude of the frictional force, which is 20 newtons. I reused the number. Okay, anyway, it doesn't matter. Times the magnitude of the displacement, 20 meters, times the cosine of the angle between the frictional force and the displacement, which is 180 degrees. And then the work done by the normal force is equal to the work done by the gravitational force, which is equal to 0. They're both equal to 0. Okay, let's go ahead and plug that into the calculator. Those two numbers are the work done by the pulling force, by the tension, is 2,719 joules, and the work done by the friction force is minus 400 joules. The total work done is the sum of all the works, which is 2,319 joules. I ask you to notice, and we're going to pay attention, we're going to do a calculation about this next time, that the pulling force is trying to speed up the sled, and the frictional force is trying to slow down the sled. It's trying to take energy away from the sled. The pulling force is trying to add energy to the sled, hence we do positive work with the pulling force. The frictional force is trying to take energy away from the sled, trying to slow it down, hence it does a negative work. And that is not a vector, those are scalar quantities, and we will relate them to energy next time.